So that's where we could stop, but it would be nice to figure out if our assumption about IB being negligible actually does hold. So what we can do is we can say, well, what's the range of HFE of our transistor? If we said, well, for the sake of argument, let's imagine I measured the transistor's HFE exactly for the transistor I was going to use, and the value turned out to be 100. Because it makes the numbers easier. Now, you'd probably find it will be in the range of 50 to 700 or something. You have to work it out for both. But just to illustrate how the working out is done, I'll only do it for one number. And if you want some practice of how to do it for several, then there's plenty of problems in the problem sheet that will cause you to do that. So we have a HFE of 100. So this means that we can write an equation for what IB will be. IB will be IC divided by HFE, which is 1 milliamp divided by 100, which is 10 microamps. Alright, so that's 1e minus 3 divided by 1e2, so that should leave us with 1e minus 5, which is 10e minus 6. So I think we're good there. In that case, we need to know what fraction IB is of the total current that passes down this branch here. So we're after what IR1 is. So we've got to get that, we can use VR1. And what the assumption that we're working under is that this is 2 volts, and we can work it out like that, that's fine. But we might like to say, well, what are the actual currents involved? I mean, this current down here, we can call this one IR1 and this one IR2, and we can say that applying Kirchhoff's law for currents here, IR2 plus IB is equal to IR1. We can say that we can rearrange this to say VB, or we could rearrange it. We write another equation. VB is IR1 minus IB times R2, and we can say that VR1 is equal to IR1 times R1, and that VS is equal to VB plus VR1. So we've eliminated IR2 essentially by rearranging this equation here. So what I did in my head was I said that a value for, because VB is IR2 times R2, and I've said, well, IR2 is IR1 minus IB, so I've did that step in my head and then substituted in. So what I should really have done is said this becomes IR2 is equal to IR1 minus IB, and there is another equation which this goes into, which is VB is equal to IR2 times R2, and that goes into there. But since I know where I'm headed with this, I'd rather just go straight to there. But if you like that continuity, that's fine. Okay. So we'll sub that and that into that to yield Vs is equal to IR1 minus IB times R2, which is that bit, plus IR1 times R1. In that case, we know everything except IR1. So we can rearrange this for IR1, and we will have, well, I'll expand it first. Vs is equal to IR1 R2 minus IB R2 plus IR1 times R1. And then I'll collect all the IR1s together and take them over so they're on their own. So we'll have Vs is equal to IR1 brackets R2 plus R1 minus IB times R2, so B. And then we can say, well, Vs plus IB R2 divided by R2 plus R1 equals IR1. Wow, that's not a very good R. Try again. There we go, IR1. So we've got a value for IR1, and we can actually put some numbers into here, and if I rub out the top bit, don't forget IB is 10 microns, notionally. So we'll do subbing into here 10 plus 10 microamps times R2, which is 20k, divided by, well, that's 100k total, so R2 plus R1 is 100k, so it's 80k plus 20k will yield IR, well, we'll write the value actually. We've got a calculator. So that will be 10e minus 6 times 20e3, 0.2, plus 10, 10.2, divided by 100 E3 is 102 microamps. Fair enough. And we can get IR2 by back substitution now, where we have IR1 minus IB is IR2. So we have 102 microamps, so it's IR2 is IR1 minus IB is 102 microamps minus 10 microamps, which is 92 microamps. 92 microamps for IR2. So if we wanted to know about VB, right at the next line. We can do VB is equal to, V is I times R, so it's IR2 times R2, which would give us 92 microamps times 20 kiloohms, which will be 1.84 volts. Now, we said that originally this would be 2 volts. We said 1.3 plus 0.7 is 2, but it transpires that the base current that we've assumed, which is 10 microamps, and that's developed from the HFE of 100. Will actually cause this base current not to be 0, but but to be 10 micro amps. And a result of that is that there'll be less current flowing down through R2, some of it will be heading into the base, and that will result in VB being only 1.84 volts and not 2 volts. And we could go on from here and say, well, that means that 1.84 minus 0.7 is only 1.14, so there won't be 1.3 across RE, which will cause this 1 milliamp not to be 1 milliamp anymore, it'll be something else. We can go round. You can, if you wish, solve the whole circuit with IB not 0, and you have to use a couple more equations than I did originally. It's a little bit more involved, but it's well worth it because it's excellent practice. So 1.84 is considerably more than 10% different from 2 volts, which would fall across VB. So what that's telling us is that if we've only got a HFE of 100, these resistor values are a little bit too large, and we might instead prefer to use 40k and 10k, because that would make this current twice as big, which would make the disturbance that IB causes twice as small, and that would mean that this voltage would head upwards back towards 2. Wouldn't get to 2, but it would get close enough to 2 for it to be not much different. I mean, 1.84 is just about 10% under, well, a little bit less than 10% under. So we'd be heading towards sort of 5% would be fine.